we've already seen how we calculate changes in enthalpy for elements, and so now look at how we can calculate the change in the enthalpy for compound formation. So forming a compound from its elements. And we saw before that enthalpy has no fixed 0 point, and that enthalpy is defined as equal to 0 at 298K for all elements. Not for all compounds, but for all elements. So if we want to find the enthalpy of compound formation, we can first think about this at 298 because that's a little bit easier. So let's say that we have a reaction where a solid metal is reacting with O2 gas to form a metal oxide. Like I said, let's say for now that this is at 298. So the enthalpy of formation at 298 is basically the enthalpy of the product, which is this. So the enthalpy of the metal oxide in the solid state at 298, and then minus the enthalpies of the products at 298. So minus the enthalpy of the metal as a solid at 298, and minus 1/2 the enthalpy of O2 gas at 298. So we know basically by definition that this term here and this term here are equal to 0 because these are just elements. And so sort of the definition of the enthalpy of formation is the enthalpy of that compound itself at 298. So these things are equal. Usually we see it in this format, but it's equal to this as well. And these are things that have to be tabulated. Well, they have to first be measured, but then they are tabulated. So we don't ever have to figure out how do we find this because this is something that we would turn to a handbook to look up. Now, what about other temperatures? So how can we find this at other temperatures? Let's consider an example. This example is for the reaction lead solid plus O2 gas reacting to form lead oxide solid. So let's look at what we have here on this chart. We have a plot of the enthalpy of the products and reactants as a function of temperature. So these lines up here, this is for lead and oxygen, so these are for the reactants, and this line down here is for the lead oxide, and so that is for the products. And these vary with temperature basically as we saw before. So for the elements, these have an enthalpy of 0 at 298K, and they increase according to the heat capacity, right? With lead, we see this step right here. This is the enthalpy of melting. So this is lead solid and lead liquid. In the case of lead oxide, we have some known delta HF at 298, and then it increases also according to the heat capacity. So for example, we have for lead, we can write this reaction that the enthalpy of lead as a function of temperature is the integral from 298 to the temperature of interest Cp of lead solid dt. And we can write an expression for the enthalpy of lead oxide solid as a function of T. And this is equal to, first, this enthalpy of formation at 298, which is 219 kilojoules per mole, and then plus the integral from 298 to T of Cp of lead oxide solid dt. Now I've not put in any n here because the coefficients on lead and lead oxide are both 1. If I was writing an expression for oxygen, I would need to remember to include this 1/2 here. Okay, so the enthalpy of formation at 298 is basically just this difference because the enthalpies of the elements are 0. But the question is, what if we want this at a different temperature? So let's say that we want this at some temperature over here around 500 K. How do we find that? Or if we want it up here after lead has melted, how do we find that? Let us look at this plot in a slightly different way then to try to answer that question. So this shows now, instead of separate lines for the reactants, just one line. So again, it's 0 at 298, and then this line here is for, you see, lead plus 1/2 O2. So this is adding up sort of the enthalpies of the reactants, and then down here we have the enthalpies of the products. We know, or can find, an expression for this pink line from the heat capacities. We can find, and I wrote it on the previous slide, the expression for this green line. We know also basically this amount here, right, from the enthalpy of formation. So if we are operating at a different temperature, let's say this temperature here, and this is the delta H that we want to find, then that's something that we can do. Let's clean this up a little bit though. Get rid of these lines. Okay, so let's look then at how are we going to do this. This amount right here, this is what we are after. So this is delta HF as a function of T. We can instead basically take the long way there. And we're going to do this in a 3-step process. This is step 1, because we know it. This is step 2, we know, and this is step 3. Okay, so we can write an expression then, and I'm going to just sort of do it in words to start with. So step 1 is delta H of the reactants. When we change the temperature from T to 298, the second step is delta HF at 298, and the third step is the delta H of the products as we go from 298 up to T. So we can then write that as an actual equation. So that delta H, the enthalpy of formation at some temperature other than 298, is equal to the integral from T to 298. So this is our first step. And we have to sum over all of the reactants of NCP dt plus, this is step 2, the enthalpy of formation at 298, and then step 3, which is the integral from 298 up to T, and we sum over the products of NCP of T dt. So I'll point out this is not multiplying by t, this is just showing that Cp is a function of t. Also, the limits on these integrals are opposite because in one case we're cooling down and in the other case we are heating up. Also, if we had a phase change present, let's say that we were considering this temperature up here instead, then we need to take that into consideration when we are calculating the enthalpy change of the reactants. So we need to include this enthalpy change of melting. But this expression down here, this is the one that we will use for how do you calculate the enthalpy of formation as a function of temperature.